Hello everybody and welcome to this monthly EURASIP webinar. And today we will have a talk delivered by Professor Ami Wiesel from Huji University, Israel. And we are very honored to have a very distinguished speaker today. And thank you for accepting this invitation, Ami. I'm a professor Esa Ollela from Aalto University, Finland, and I will be moderating the webinar today. So before I introduce Ami, I would like to have a few words about the format of this webinar. So first of all, the webinar is being recorded. So that's why I would like you to be muted during the talk. And at the end of the talk, we will have a questions and answers session. And you can open your microphone at that time. And we will also stop recording when the questions and answer session starts, so you can freely talk. If you do not wish to speak, you can also send your question in the chat, and then I will make sure that Ami tries to give some sort of answer to it. So let's introduce the speaker. Professor Ami Wiesel received a bachelor degree and master's degree in electrical engineering from Tel Aviv University, Israel in 2000 and 2002, respectively. He obtained the PhD degree in electrical engineering from Technion, Israel Institute of Technology in Haifa, Israel. That was in 2007. He was a postdoctoral fellow in the University of Michigan, Ann Arbor, during 2007 and 2009. He's currently a professor in the Rachel and Selim Benin School of Computer Science and Engineering in the Hebrew University of Jerusalem, Israel. Dr. Wiesel has done some very fundamental research in wireless communications, in statistical signal processing, estimation detection, which is actually the talk today. He has written a book on covariance matrix estimation called Structured Robust Covariance Estimation, which was published by Foundations and Trends in Signal Processing. It's a very excellent book. I recommend everybody to read that book. He was a co-author of the paper Learning to Detect, which introduced a deep learning architecture called DetNet. It was published in IEEE Transactions on Signal Processing in 2019, and his student received IEEE SBS Young Author Best Paper Award for this work. So without further ado, I would like to give the floor to Professor Wiesel. Today's talk is called Deep Learning Solutions to Estimation and Detection.
Thanks a lot, Esa. It's fun to be here, and thank you for inviting me. Let's see. Okay, so I'll start again by thanking EURASIP, Nelly, and Esa for the invitation. So you mentioned the Best Paper Award. So this is the student, Zvi Diskin, and there was another student, so I also got it. And actually, some of the works, most of the work in this talk is also by Tzvi, who did a lot of the stuff, also with Iftach, Yoav, Daniel, and collaborators Uri and Yonina, and we got funding from Google and ISF. So let's see what the talk is about. So I think in the last, I don't know, 5, maybe more years, what I'm doing is trying to see how we move from old classical machine learning, from old classical signal processing to machine learning. And for me, like when I was a student, or we used to call it the Bible, was the book on the left here by Stephen Kay, The Fundamentals of Statistical Signal Processing. That's where I learned everything. And I guess today most students don't use that book, but they know books on machine learning. And on the right here, you have the book of my colleague, Shtai Shalev Schwartz, on understanding machine learning. And I think everyone is doing this transition, and this is what the talk is going to be mostly about. So let's like just see the terminology, see how things are called, used to be called and how they are called today, and what are the differences. So we used to have a, do you see my cursor, my mouse? Essa. Okay, I'll assume you do. So we used to have a model, and today we have data. We used to have problems in estimation, and today you call it regression. We used to have problems in detection. The difference between estimation and detection was whether we are estimating something in the reals or something binary or something discrete. And in machine learning, that's the difference between regression and classification. We used to have algorithms, and today everybody uses neural networks. And the two more technical differences that at least in my, not everybody in signal processing, but I think most of the people in signal processing used to be mostly non-Bayesian. And today machine learning is by definition always Bayesian. And everything used to work for all theta, for any parameter. And today in machine learning, things only work well if the train is equal to the test on some prior distribution. So that you'll see most of the talk is somehow how to do machine learning such that it will work for all theta and not only when the train equals test. Okay, so machine learning, I guess so everybody's doing machine learning, and there are lots of things you can do there. I think what I'm going to talk about mostly is losses and metrics. So basically, what is machine learning? You get some training set, you minimize the loss on it, and then you evaluate some metric on the test set. And I think that's like the main decisions when you do machine learning is how to get the data. I'm not going to talk about it a lot. How to choose the architecture. I'm not going to talk about that too. And then come the two questions about the loss and the metric. The metric depends on what you really want on the application. And the losses are like friendly approximations of the metric. Think of it as like smooth approximations of the metric. And this talk is going to be on what are the interesting and important metrics in statistical signal processing, in estimation and detection. What are the metrics? And then what are the losses that are good for optimizing these metrics? So this is what I'm going to talk about. Now, I promised in the abstract two parts, and that's the first two parts in this talk. But I added these are older, like from a year and a half ago we finished them, or a year ago, and I added now a third part, which is this is the first time I'm talking about. So but you see, all three parts of this talk are basically about metrics in estimation and detection and how to approximate it. In estimation, we'll discuss bias, variance, and MSE, which are the classical metrics in parameter estimation. And in detection, we'll talk about false alarm and detection or misdetection rates. Then at the end, we'll talk again about estimation and hear about MSE, SNR, and KL. I hope we'll get to the covariance estimation because this is really new and very exciting for me. So let's start with the first part on estimation. So again, as I said, now I'm going to talk about bias, variance, MSE, so the classical metrics in signal processing, and how you address them using machine learning. So classically, the classical problem if you open casebook about parameter estimation, we get X, which is an observation, which is distributed according to X and parameterized by Y, which is unknown. And we want to estimate Y and have some Y hat as a function of X. That's the goal. You get X and you want to guess what Y is. How do you check if your estimate is good? There are usually three metrics you can use. The bias, which says that on average, on expectation, how far is your estimate from the true Y? The variance talks about how the estimate fluctuates around its mean. And the MSE, which is the variance plus the squared bias, tells you how it counts the expected square error of the distance between Y hat and the true Y. The important thing to notice in all of these three quantities, and I write it here, that they are a function of y. Okay, the bias, the variance, and the MSE are all a function of y. Okay, so every different y, every different unknown, we're going to get a different MSE, a different variance, and a different bias. And these are the classical non-Bayesian metrics. There is also a different approach, which is called the Bayesian statistics, and they usually assume a prior on y, and they have a different metric, which they also call it MSE. I will call it BMSE too, so we will know the difference between this MSE here and the Bayesian MSE. And the difference is that this is an expectation over y. Okay, so this is no longer a function of y because we took an expectation, we took an integral over y, and now this is a number. It makes life much easier for the Bayesians because they just need to minimize a number, which is much easier. But on the other hand, they need to know what the prior is, and that's why they need either prior knowledge or a training set. So this is basically the difference between Bayesian and non-Bayesian statistics. Now, what were the classical solutions? The non-Bayesian people had a big problem. They cannot minimize the MSE directly. Why? Because we don't know, the MSE depends on y, and we don't know why. So what they usually do is they do maximum likelihood, which is they maximize the likelihood. And there is a well-known result that if you maximize the likelihood, then asymptotically, this minimizes the variance, assuming that you are among all the unbiased estimator. So it gives you both minimum variance and zero bias for all y. And for all y is very important. When we say unbiased estimator, it means that no matter what the unknown is, if we do the experiment 1,000 independent times and average over them, on average, we're going to be correct. Okay, that's the bias. The expectation of y hat is going to be exactly y. We do the experiment lots of times. So these are the non-Bayesian people. And again, as you see, they only know how to solve the problem using maximum likelihood in the unbiased case. On the other hand, the Bayesian people, what do? Their MSE, the expected MSE, is just a number, so they can minimize it. When I was a student, we always said that this is intractable, nobody can solve this. But today, I think the big deep learning is exactly this. This deep learning is a way to approximate this optimization. You do the expectation using a training set, and you do the minimization using SGD. And y hat is a neural network. So today's world is mostly Bayesian, and our talk is going to be how can we take the Bayesian approach and make it behave more like maximum likelihood and guarantee things which are good on for all y and not on average on y. Okay, so my solution, and you'll see most of this talk is actually very, very simple. I think the most important idea here is that in today's world, things changed. And now if you want to do something, just state it clearly and do it. Before we had to do approximation. Today, you just need to state exactly what you want. And then you need a very talented student like Tzvi who knows how to solve optimization problems using deep learning. But the hard part is just, I mean, that's something technical. The fundamental part is just state what you want. So in standard machine learning, this is standard regression. We try to minimize the expectation between y hat and y. In bias constraint estimation, which is our paper, what you do is you also add a constraint on the bias because we want to be unbiased for all y. So we have a constraint here. And we say that on expectation, we want to say that the bias is 0 for any y. But if we say that an expectation of something positive is 0, it means that for every y, it's 0. And then this optimization should theoretically give us something very similar to maximum likelihood, right? At least asymptotically, right? Because it's going to minimize the variance or the MSE subject to a bias constraint. And indeed, Sarah says that BC is asymptotically an MVUE. for any prior, doesn't matter, any reasonable prior, wide prior that is not singular that you're going to choose. If you have enough data, you have a large enough, expressive enough neural network, and you are asymptotic in the statistical sense, then any deep learning algorithm with the BCE objective is going to converge to the MVE and give you exactly what maximum likelihood used to give us. Maximum likelihood was also asymptotically minimum variance and unbiased and achieves the Camero. So this for me was very exciting because it's like it's the first time I saw how to fill in the gap between deep learning and maximum likelihood. How do you do that? If you want to do deep learning and get something close to maximum likelihood or approximate maximum likelihood because maximum likelihood is too expensive, all you need to do is do regression, but add this little constraint here, and then you know you're going to be an MVE, if such an MVE exists. There is one case where it's actually easy to compute the maximum likelihood and also the neural networks, and that's the linear case. And we're talking about the linear case, where both our model, our observation model X, is a linear function of Y, and our estimator Y hat is a linear function of X. In this case, we can compute the BC, the bias constrained estimator in closed form, what you have here. And you can see, and you can compare it to the two, for me, I think when I teach statistical signal processing, the two most important estimators in linear parameter estimation are these two extremes. In the linear Bayesian MSE is this thing, where the estimator is just the cross covariance times the inverse covariance of the observation. And on the other extreme, if you're not Bayesian, then you do least squares and you get this well-known formula. Our BC gives you something in the middle. If you take C equals 1, then this falls, and you get exactly the Bayesian linear MMC. If you take C equals 0, then what do you get? This falls, and you get weighted least squares. So basically now we can do an estimator, which is half. You can choose how much Bayesian you want to be. You can be fully Bayesian, fully non-Bayesian, like least squares, and go anywhere in between them. And you can also do it non-linearly and do very sophisticated things. You're using deep learning. So how do we do it in the non-linear case? In standard linear regression, we have a training set and we minimize the MSC regression loss, the L2. In BC, we do exactly the same. We have the regression loss here, but we add lambda plus a squared bias term. And that makes a lot of sense, because we just want to penalize the bias. And now the hard thing is that to estimate the bias, you see you have two expectations here. Here the expectation is both over y and x, here too, in the regression. You have for every xi, you have yi. In order to compute bias, we need for each unknown to have multiple observations because we want to estimate the bias. So we need lots of xij's for every yi. And then we can compute this part. So that's like the hard part of doing it. And at the beginning, we thought that's going to be very hard, but apparently it's very easy. And here I see two options. Some people use synthetic data. I mean, if you have a model, and that's what you usually had when you did maximum likelihood, so you can just generate as much data as you want. So just generate y's, and then for each y, generate a lot of x's. But sometimes you want to do it using real data. And then you have one picture of a horse, and you want to make sure that you want to get lots of pictures and still understand that this is a horse. And people do that all the time. They do it in computer vision. It's called data augmentation. You take the horse and you start flipping it around, and lots of rotations and all kinds of augmentation. And you get lots of x's for the same y. And now you can easily compute the bias and add it to the loss. So let me show you a more interesting problem. So this is a classical, as I said in the beginning, I mostly work on covariance estimation. And covariance estimation is a problem when you have structure. It's quite hard because computing maximum likelihood can be challenging. It takes a lot of time. Maximum likelihood is usually great, but it takes a lot of time. And also there's a problem of initializations and stuff like that. So we would like to be able to replace it by a neural network that doesn't need to any initialization and is going to run faster. Now, I like to talk to people. Here it's in Zoom, but I'll still ask a question if one of you wants to answer. So I'm showing you here two pictures, two photos of the figures of the performance. Now, what you see here are just like errors. This is MSC, and this is MSC. And the y-axis, I just ordered it so it would look nice. Now, what we have here is the orange. Orange is the neural network, a regular neural network. Green is the camera bound, and the blue is our bias constraint estimator. Now you see here two figures. Now the answer is actually, usually I ask, what is the difference between the top and the bottom? And the answer here is clearly that in the top graph, the test is exactly equals to the train. And what happens here? When the training distribution and the test distribution is exactly the same, deep learning, which is the orange, is amazing. Okay, I really believe if you have a training set, which is exactly like the test set, then I think nothing is better than deep learning. Deep learning is just the best solution there is today. And you see the errors are really, really small, much better than our estimator and much better than the camera. Now I usually ask how camera bound is a bound on the lowest MSE. So how come the deep learning is better than it? If someone wants, they can answer. Or not. Okay, so the answer is clearly, oh, Esa? What?
Over-parameterization, right?
No. The reason here is that, hey, so good. The reason here, I'm asking why on the top, how can the orange deep learning be better than the camera?
It is biased.
Of course. Yeah, it's completely biased, and it's biased towards the training distribution, and it's much better on the training distribution. And when the test is the same, we are also the best. So if training equals test, then you can beat camera bound, and you are unbiased. You are biased to the training set, and you are amazing. The problem is what happens when the test is a bit different. Suddenly here, you see that the deep learning starts to suffer of distribution, whereas we, the blue, stay on the camera bound. And all we did is we took the same network, we only changed the loss. Instead of just minimizing MSE, we minimized the variance plus lambda bias squared. So I thought that's kind of nice. And I think this really gives you the full picture and the truth. And now the question is, what is better? Depends on you. If you believe that the test is going to be the same as train, do regular regression. Otherwise, you're going to pay a price. You're only going to be able to achieve the camera, but you can be much better using a very, very simple trick. Okay, let me show you another example. This is with real data. I like this curve. We tried this algorithm on a localization dataset. And I think this also shows you exactly the advantages and disadvantages of unbiasedness. Okay, what you see here, this is a localization test. Same algorithm. We have here 3 realizations. The blue is the ground truth. The red is a regular deep learning network, and the green is the same architecture. Everything is the same, only we had a bias constraint. Which is better, the red or the green? What would you prefer? I'm giving you a circle around the circle. Which estimator do you think estimates the ground truth better? Okay, I will answer. The red is clearly is smaller. Okay, it gives you a smaller errors. You see, all the red ellipsoids are much smaller than the green ones, and also in the numbers on average, you see the MMSE gives you a smaller MMSE than the bias. But what is nice about the green one? The green one is I took the average of a few expectations, and look what happens. The blue ground truth is always exactly in the middle of the green ellipsoid, which is exactly the meaning of unbiasedness. Now you can just you look at this curve and you can show this to the client and ask them, what do you prefer? Do you want to have small MSC, or do you want to promise that you're always in the middle? I actually showed this to a few customers who we collaborate with, and they all said they prefer the green one. They don't mind having a larger MSC, but they do like the fact that the truth is always in the middle. But again, it depends on the application. So this exactly shows you what is bias versus MSC. Okay, so this was part one. Let's see, 26 minutes. Okay. So now I'm going to show you the next work. Actually, almost exactly the same as before, only now in detection. Before it was estimation, now I'm going to talk in detection. If before the trade-offs were usually between bias, variance, and MSC, in detection, the trade-offs are usually between false alarm and detection. So let's start again. The problem, and how did people do it in the classics? Now, how do people do it in the deep learning world? So here is a classical hypothesis testing, target detection, X, the observation, are distributed according to some X. We have two options, 0, no target, 1, there is a target, and there are nuisance parameters Z. Okay, so for example, you can have a steering vectors times Y, which is 0 and 1, plus noise, and sigma is an unknown nuisance parameter. Okay, so the unknowns here is Y equal to 0 or 1. That's what we want to detect. And there is also a nuisance parameter, which is sigma, which we don't know. Now, the non-Bayesian metrics, the classical statistical metrics for hypothesis testing, are detection rate and false alarm. Detection is when we guess that Y hat equals to 1 and the true Y is equals to 1. False alarm is when we estimate that Y hat equals 1, but Y equals 0. And that's a false alarm because we said there is a target when there is no target. And one of the important things to see that practitioners, like real engineers, usually want is they want an estimator which is CFAR, that has a constant false alarm rate, which means that the FPR is equals to alpha, no matter what the sigma is. That's important because that's how you're going to set the threshold. In reality, you don't know the variance of the noise. So a test which is CFAR or a detector which is CFAR gives you the same false alarm for any noise variance. So these are the non-Bayesian approach. The Bayesian guys, they have no difference between false alarm and detection. They just put a probability on Y. Let's say that Y equals 50% of the time 1, 50% 0, or maybe unbalanced. And they look at the expected value of the error. And that's much easier to handle because, again, this is a number. It doesn't depend on the true Z. Okay, let's talk about the classical solutions. So the non-Bayesian people usually do likelihood ratio test, LRT, which is optimal. And this is when there are no nuisance parameters. If there are nuisance parameters, then you just estimate them using maximum likelihood, plug them into the LRT, and this is called the GLRT. And this is known to be asymptotically CFAR. Now, it's basically LRT with an estimated nuisance parameters. This, I think, is probably the most common test detector or in statistical signal processing, and then there are lots and lots of variance, approximations, stuff like that. On the other hand, there are the Bayesian people. The Bayesian people, as I said, they chose a prior, and they try to minimize the average probability of error. They get the stain, and actually they just marginalize the probabilities with respect to all the possible unknowns. And it depends on the priors they chose. Okay, if they choose the right prior, then they're going to be really good. Otherwise, they might fail. But at the end of the day, you see that GLRT and BLRT look very, very similar. GLRT chooses the maximum in every option and then divides them. BLRT takes the integral that depends on some prior and divides them. Now the question is, and of course, what does deep learning do? Deep learning does Bayesian. Okay? Deep learning, what do? They solve this problem here. They try to minimize the probability of error. They take some surrogate function of the probability, let's say the cross entropy, and they take some surrogate, some approximation of all the functions T, and they call that an architecture, and they find within the class of some architecture, what is the neural network that minimizes the cross entropy, or something like that. Now the question is, how is that related to GLRT? So this is the theorem which we have, and I was very, very excited about this theorem. I think for me, that's one of the things I think probably the work that I'm most proud of so far in my career. So let's start here actually before we define CLRT. So I think it's very easy to see that in simple hypotheses, the Bayesian LRT and LRT are exactly the same. This is very easy to see because the only difference between them is the nuisance parameters. Here you see the BLRT versus LRT. And GLRT is just a function of the nuisance parameters here. So that's the main difference, and it doesn't matter. And that's why deep learning works great here. But what happens when you do BLRT in general, it's going to get really good results, but it's not going to be CFAR. It's going to give you a very good probability of error, but it's not going to try to balance. It's not going to try to balance the false alarm between all the possible nuisance parameters. Our main result is that theoretically, if you minimize the probability of error, but you add another constraint that your estimator must have constant false alarm, then asymptotically, otherwise you don't know anything about these things, and using an assumption which maybe someone will be able to remove, which is a block diagonal Fisher information, which usually holds in all the examples we saw, but here we don't know how critical it is. Then we can show that the BLRT, if you add any Bayesian likelihood ratio test, if you add a CFAR to it, constraint, then this is exactly GLRT. And I was very happy about it because before that, I didn't even know what is the optimality of GLRT. In what sense is it optimal? I mean, for me, it was always like, there is LRT. When you don't know the nuisance parameter, just plug in the maximum likelihood. Now we see, and we know that it's also asymptotically equivalent to many tests like Rao and WORLD. But who knows, are these estimators optimal in any sense? I didn't know that, and now we know. GLRT is actually the best thing you can do if you add a CFAR constraint. And by the way, all of this, it doesn't say here, it doesn't matter which prior you work on. Okay, for any prior, if any prior which is non-zero, of course, if you add a CFAR constraint, then GLRT is exactly the best Bayesian thing you can do. So, okay. How do you do it in practice? This is a very short slide, but this is a year of work. To add a constraint, you need to add alpha and some penalty here. This is like a little gun or MMD. If you want, we can talk about it later. But that is something technical. It's hard. It's not something easy, but it's technical, so I'm not going to discuss it. That's what I have good students for, to be able to solve such optimization. But theoretically, I mean, you can take the regular classifier and add another penalty here that ensures false alarm. Okay, so let's see what happens. So let's start with the sanity check. The easiest problem, detection in Gaussian noise. Gaussian noise with an unknown variance. You just want to know if A equals 0 or not 0. The amplitude is unknown and the variance is unknown. Now I'm going to show you here 4 detectors. There's the match filter, which is very, very simple and easy. It is optimal in the ROC, but it's not going to be CFAR. You see, because it depends on the noise. Each time it's going to get a different, the false alarm is going to change. Then there is the GLT, which people usually use. They prefer the GLT. It loses slightly in the ROC, but is generally close to optimal and is CFAR. Okay, and how does it do it? Because it normalizes by X transpose X. You see, so you've got X squared both in the numerator and the denominator, and they cancel out, and that's why you get a CFAR result. Then we have the regular deep learning. It's going to be amazing in terms of ROC, but not CFAR. And if we add our constraint, then you're going to be good in ROC and also in CFAR. Let's see in the graphs. So here is the ROC, the ROC curve. This is in logarithmic FPR because that's what people are usually interested in. And you see that all the Gaussian GLRT, the BNet and the CFARnet, they all perform almost the same. BNet is a bit better than everyone. In general, deep learning is amazing. Okay, deep learning is really, really good in terms of accuracy. But the problem is, what happens if you look at the FPR as a function of the FPR, a different noise variance? And what do you see? You want to be on the diagonal here. You see the Gaussian GLRT is exactly on the diagonal. It's completely invariant to the sigma. The deep learning approach is really, really bad. And CFARnet is very close to the diagonal. Now, I should tell you, up to 10 to the minus 2, we are almost exactly. The reviewers in this paper asked us to be close to 10 to the minus 3. This is really a hard problem. Being CFAR in very low false alarms is hard, but you see how much better we are than regular deep learning. You'll see that all over, and maybe and then we can discuss it. All of our problems these are hard optimization. There is a price for it. Okay, it takes time, takes a lot of learning, big networks, but you see it's very, very clear how we are CFAR or close to CFAR, and regular deep learning isn't. But this is stupid. Why would we want to do a neural network when we have a simple GLRT? So let's do the same now in a non-Gaussian case. So now this is still a non-Gaussian case where everything is known. So it's a GMM. So GLRT is solvable using EM. It's just very slow. So you see the GMM of GLRT gives you perfect talk, perfect CFAR, but it's very slow. Neural network is going to be great in ROC, but not CFAR and fast. CFARnet is going to give you the advantages of all. So again, in the ROC, you see the best is always the neural network. We are slightly worse. We pay a price for CFAR. But if we look at the FPR versus FPR, you see that we are very, very close to the diagonal, just like GLRT, whereas regular deep learning is far away. Let me show you one more example. This is an example in correlated noise. Here, I'm not going to go into the details. If you want, can I talk later? It's basically you're trying to estimate the covariance, and then you plug it into the GLRT. The classical estimators are Kelly with diagonal loading. Here, the BNet is the deep learning, and CFARnet is us. Again, in the ROC, BNet is the best. Then I think Kelly, probably the diagonally loaded Kelly, and Kelly is bad, and so is CFAR. But the differences are very small. If you look at CFAR, FPR versus FPR, you see that Kelly is CFAR, but the diagonally loaded Kelly is very not CFAR. The neural network is not CFAR, and we are close. Again, getting to 10 minus 3 CFAR is a hard problem. Okay, I say I'm not going to have time to talk about the, I just mentioned the last talk, but I do want to talk about a bit about the machine learning literature. Everything I talk today is not something new in machine learning. Okay, I think it's and it's important to put it in context. There is a lot of literature these days on fairness and out of distribution generalization in the machine learning community. I think that in some sense, statistical signal processing, especially non-Bayesian statistical signal processing, is like the extreme case of out of distribution and fairness. Okay, we want to be fair not only on 3 groups, on let's say males and females, but over any possible Y. We want to be to work to generalize well out of distribution for any possible theta, and so it's very related to the same works, and we can take ideas from them. They call it. There's also, these are different literature, but the ideas are very similar, both fairness and OOD. Some people talk about equalized odds. One thing which I think is interesting, and I didn't see anybody mention before, I'll be happy if you know of someone, then let me know. In machine learning, they often talk about fairness. They want the algorithm, the classifier to work well for Swedish people, Israeli people, and German people. And when they say they want it to work well, they mean all the errors want to be should be the same. That's what they want, equalized odds. It's interesting that in our case, it's we are not symmetrical in signal processing. We treat the detection probability and the false alarm probability differently, and it's not common to ask a detector to have an equal detection rate. What we usually want is constant false alarm. So in that case, our problem is easier, and that's good because ensuring fairness has a price. It's costly. So, and we only need to ensure fairness on one side, only on the false alarm, not on the detection side. So that's interesting. You have here some references, and I'll just mention the last work. So as I said, this was all about metrics and losses. The last 2 works were about bias bonds and MSE, and now I talked about false alarm in detection. And again, in each one of them, I just changed the loss a bit to behave more like what I'm really interested in. In the case of estimation, it was to be unbiased. In the case of detection, it was to be CFAR. Now I'm going to talk about the thing that I usually work on, covariance estimation. And both me and I know Esa and Sergey probably too, we all did a lot of work on covariance estimation, and we usually use MSC. And I was wondering, and this is a work which was just published, I was wondering what is the right metric for talking about covariances. Now, suppose you have some C and you have an estimate, C hat. How do we measure the distance? So most of the works, due to simplicity, and by the way, my works too, most of my works too, always use MSC and norm-based distances, like the Frobenius norm or the spectral norm. Whereas if you look in statistical literature, they usually use Kullback-Leibler. And there are like zillions of work. MSC is much easier to handle. Of course, here you have the trace, the inverses. And I wondered which one is better for our problems in detection. So I won't go into the details, but when you go back into the history and you start reading what did people usually do in the detection back in 1974, a year before I was born. So this is the famous paper by R&B, and they defined something called the NSNR. It is the normalized SNR. They said what you want is actually the SNR is we want maximum SNR. If we had known C, then we would get this SNR. We're going to get a lower SNR because we're using a wrong C hat. And if we look at their normalization, their ratio, then it tells you exactly how much do you lose in SNL because you use an estimate instead of the true C. And their famous rule of thumb was that if you use the sample covariance, then no matter which target is X, you'll need the number of samples, and you want the SNL to be NSNL to be 1/2, then you need twice the number of the dimension samples. So if the dimension is 20, you need 40 samples. And I think that was what most people did back then. And there are billions of work trying to improve that, use the diagonal loading, other targets, and all kinds of extensions. But I think the big problem in this formula here is that the NSNL depends on C hat and C, and depends on S. So the question is, which target should we use? If we know the target, then yeah, that's easy. But usually we don't know the target in advance. So what we try to do here is we said, okay, let's look at the worst case target. Let's look at the NSNL of the worst possible target. And we have a nice closed form solution to it based on something called the Kantorovich inequality. And that's really nice. It's not amazing, but it shows you exactly how to compute the NSNL of the worst case target. So we thought this sounds like a good metric to work with. Okay, and you see it depends actually on the ratio between C hat and C of the inverse using their eigenvalues. So that's really nice. But what is really cool in my view is the next result is that statisticians usually, as I said, use Kullback-Leibler. And indeed, Kullback-Leibler also can be written in terms of this ratio. And what we show is the KL is exactly a sharp upper bound on the log NSNL. That's the log is actually really cool because even if you look at RMB, you see they talked about in the Bs because they also took the log. And the log NSNL is actually almost exactly the DKL and is bounded by it. So if you minimize KL, you maximize NSNL. And this is not true for MSE. Okay, MSE, you can take MSE as low as you want, while the SNR is really bad. And this is just the time to show the graphs. So what we show here, let's look at the top here. Here it's more, this is synthetic data, so it looks good. So we tried two estimators, one using KL loss and one using an MSE loss. And then we evaluated using 4 metrics. The metrics are MSE, KL, worst NSNL, and the AUC. AUC is, I think, if you ask the clients, the people who read the real engineers who work, they don't care about NSNL, they don't care about KL, and they don't care about MSE. They usually care about AUC. AUC is the area under the ROC curve. That's like that. This is what really gives the money. Okay? And what you see here, let's look at the first two. You see that when you optimize MSE, MSE is really good and KL is bad. When you optimize KL, KL is very good and MSE is very bad. So these two behave exactly the opposite as expected. But as our theorem shows, the worst cases NSNL and the AUC behave very, very similar to KL. And of course, the NSNL or AUC, these are metrics. You cannot optimize them. You cannot do gradient descent on AUC. I mean, people do that, but it's very hard. And the same for NSNL. These are eigenvalues and stuff like that. But KL is quite easy, okay? And you see, so I think the result, my conclusion from here is that if you want to do deep learning or any other kind of loss optimization, and your goal is AUC, don't use MSE, use KL divergence. Here is the same on real data from Pavia University. Here, you see again that AUC and the NSNR look very similar to KL. MSE is not the same. And again, you see that KL performs better than MSE in this case. The surprising thing here, and this depends on the data, but I wanted to say the truth, that here it does, unlike what you would expect, KL is even better than MSE and MSE. But this really depends on the data. So don't take this for granted. But I think what is I always saw is that AUC behaves more like KL than it does to MSE. And that's it. Just on time, I think. I think deep learning is fun and great, but don't forget the classic. If you want to get a regressor to have more classical properties like MLE and MVUE, just add the bias penalty. If you want a classifier to be more safe and better for detection, add CFAL. And talk to your customers, understand what are the metrics in your applications, and choose the right loss. And that's it. Thank you.
Thank you, Ami, for excellent talk.